Hello everyone, welcome to Chapter 8. This chapter is about optimization, but not optimization as a clean mathematical exercise. It is optimization as a daily struggle between a model and the complexity of reality. In many ways, this chapter explains why training deep neural networks is hard even when everything else looks correct. If probability was the language of uncertainty and regularization was the art of restraint, then optimization is the engine room of deep learning. This is where learning either happens or silently fails. And let me say this clearly at the beginning. Most deep learning failures are not caused by bad ideas, weak architectures, or even insufficient data. They fail because optimization breaks down. So what does optimization mean here? At its core, optimization is the process of adjusting model parameters to minimize a loss function. In plain language, we are searching for parameters that make the model's predictions as close to reality as possible. But here's the catch. Deep learning optimization problems are non-convex, high-dimensional, and filled with saddle points, flat regions, and deceptive valleys. This is not a smooth landscape. It is rough terrain, and navigating it requires more than blind mathematical faith. The chapter begins by reminding us that gradient-based optimization is the backbone of deep learning. Without gradients, there is no learning. But gradients themselves are fragile. They can vanish, they can explode, or they can point in directions that look promising but lead nowhere. Sometimes they tell you nothing at all. Gradient descent, in its simplest form, updates parameters by moving in the direction of the negative gradient. This sounds simple, almost elegant, but simplicity does not mean ease. In deep networks, the loss surface does not guide you gently to a single global minimum. Instead, it confronts you with plateaus, cliffs, and saddle points. One of the most important insights of this chapter is that local minima are not the main enemy. In very high-dimensional spaces, most critical points are saddle points rather than true minima. This explains why training often stalls. Not because the model is optimal, but because it is stuck in a flat region where gradients are weak. This is a subtle but crucial shift in how we understand failure during training. This is where optimization algorithms start to matter deeply. Plain gradient descent is rarely enough. Momentum accumulates past gradients and smooths the optimization trajectory. Instead of reacting nervously to every slope, the optimizer gains inertia. Think of pushing a heavy object. A single push barely moves it, but repeated pushes in the same direction build momentum. Adaptive learning rate methods like AdaGrad, RMS-Prop, and ADAM go even further by adjusting step sizes based on historical gradients. They recognize that different parameters learn at different speeds, and they adapt accordingly. However, the chapter is careful to warn us. Adaptive methods are powerful, but they are not magic. They can converge quickly, yet sometimes generalize poorly. This tension between fast convergence and robust generalization becomes a recurring theme in deep learning practice. Optimization success is not just about speed. It is about where you end up and how stable that solution truly is. Another central idea is the learning rate. If the learning rate is too small, training becomes painfully slow. If it is too large, the model oscillates or diverges entirely. There is no universally correct learning rate. Optimization is not a fixed formula. It is a negotiation between speed and stability, between exploration and precision. This is why learning rate schedules matter. Decay strategies, warm-up phases, and cyclical learning rates allow the optimizer to behave differently at different stages of training, encouraging bold exploration early on and careful refinement later. Initial is another silent hero of optimization. Bad initialization can kill learning before it even begins. If activations explode, gradients lose meaning. If they vanish, learning freezes. Proper initialization preserves signal flow across layers and maintains variance. This is why strategies like Xavier and He initialization exist. They are not aesthetic choices. They are survival mechanisms for deep networks. Batch size introduces yet another trade-off. Small batches introduce noise, while large batches reduce variance. Noise can slow convergence, but it can also help escape saddle points. In this sense, stochasticity is not merely a flaw, it is sometimes an advantage. Randomness injects exploration into the optimization process, allowing models to discover better regions of the loss landscape that deterministic methods might miss. And here comes a key realization that fills the final gap of this chapter. Optimization in practice is never perfect. Gradients are noisy, estimates are approximate, and computation is limited. Yet deep learning works. Why? Because optimization is not about finding the best possible solution in theory. It is about finding a solution that is good enough, stable enough, and flexible enough to generalize to the real world. Lower training loss does not guarantee better intelligence. The loss function is only a proxy. What we truly care about is performance under uncertainty, in environments the model has never seen before. Optimization is necessary, but it is never sufficient on its own. By the end of this chapter, you stop thinking of training as a mechanical process and start seeing it as a delicate interaction between mathematics, data, and computation. Let me end with a reflection. Deep learning optimization teaches us humility. Even with massive models, powerful hardware, and sophisticated algorithms, learning remains fragile. And perhaps that is the most honest lesson of all. Intelligence, artificial or biological, does not emerge from perfection. It emerges from navigating imperfection. In the next chapter, we will see how optimization interacts with practical engineering constraints. But for now, remember this. Training deep models is not just about minimizing loss. It is about understanding the landscape you are moving through. I am Sadi Evren Seker, and I share the core knowledge that truly matters in the age of artificial intelligence. See you in the next chapter.